Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be finishing Chapter 5, and we'll learn how to write out model equations and interpret model coefficients for factor models. So here we are in Chapter 5. We'll go over to the PDF. And as a background, let's recall the Beatles data set on the original scale of hours 10, where we fit an interaction model, and we calculated cell means for every combination of dose, low, medium, and high, and insecticides, A, B, C, and D. Those means are plotted as the big symbols in this plot, and we want to use our statistical model, our regression model, to estimate those coefficients. So I'm going to scroll on down now past a whole bunch of stuff, and we fit, there we go, we fit the model here with linear model, hours versus the main effects of dose insecticide, and here's the interaction term. And we looked at the type 3 sums of squares in the Anova table to ask which terms are significant. In this case, the interaction was not significant, though we also later found out that there was issues about non-constant variance in this situation. But I'm going to ignore that for now. I want instead to look at this other table that we've been jumping over every time, the summary table that gives the parameter coefficients. So I'm going to scroll down a little bit, and in this table we have this column of estimates. So it's this column that we want to be able to interpret. In particular, we have the intercept, which is the baseline group for all the factor levels. And in this case, because we see the medium and high doses here, which are offsets from the baseline group must be the low group. Similarly, for insecticides, the baseline group is the A group because it's not represented here. In R, the default baseline group is the first group in the list, or the first level in the list of factors. Yeah, I actually want to use the word level. So we've got factors, so dose is a factor and insecticide is a factor, and the levels of dose are low, medium, and high. The levels of insecticide are A, B, C, D. We also have these interaction terms down here, and for each of these effects we have an estimate. So this estimate, 0.412, is actually the mean for the low dose group of insecticide A. And everything else here are offsets from that intercept. So our goal is to be able to write out the statistical model equation in such a way to interpret or to either use these values to get back to what the means are for all the values in the table, or work the other way. If I give you the values for a table of means, could you actually calculate what these estimates are? And it turns out if you can add and subtract numbers, you can do this. So we're going to try something new now. Here's a piece of paper, and here's my pen. So your point of view, just so that you understand why this might look the way it does, is you are about the distance of a pen from the piece of paper. And an unfortunate consequence here is that you're going to see lots of close-ups of my hand. But that's the way I figured out how to do this. And if you could see my kitchen counter right now, you'd see that I've gone through a major effort to try to record a piece of paper. Okay. And let me chop that. So our goal today is basically to look at models of this form. Let me reform this. yi, which are our individual observations, is going to be written in terms of the center for yi, basically the predicted value, plus error. And we know that our error terms follow some distribution, okay? For example, the errors are normally distributed with mean 0 and a common standard deviation sigma squared. And those are assumptions that we care about in the model. In this lecture, we're going to focus on the center. How do we write the center in a way that we can interpret those tables that we get from R or SAS or any other statistical software? So we are going to approach this by, if I jump in chapter 5 to the very end, section 5.5, writing model, factor model equations and interpreting the coefficients. So we're going to look, I'm going to give you just the one sample t-test to start with. Then we'll look at one-way Anova, two-way Anova without interaction, and then two-way Anova with interaction. And so these tables here are the estimated values, y hat, and we want to write a model equation based on those. And if you want to follow along, here in the footnote is a link to a reference sheet for these examples. All right, so here we are, plain piece of paper. So let's look at a one sample test. Recall. We would typically use something like the t-test to ask questions about a hypothesis, whether mu equals a hypothesized value, mu not. We can also create a confidence interval based on the t distribution, which has y bar plus or minus a margin of error, okay, which is a t critical value from the t distribution times the standard error of y bar. All right, and we know this to be s divided by square root of n. Okay, no big deal. All right, so what our goal here is, we've got data. Let me see, make a little more room. So say we have some data. That are centered at 5. So we collect some data. There it is, okay? And that mean is 5. So that is y bar. So in terms of this model up here, yi equals center plus error, how can we write the data that we observed? So yi equals some center, which we'll just call mu for now, plus error. And notice I've got subscripts I for yi and ei, because those are different for each observation, but mu is the same. And so what we want to do is rewrite what mu is in terms of betas. And in this case, just beta naught. It's the intercept. Okay? In terms of x, there's no real x here. It's just a particular group, group 1. Right? We've got one sample from one population, and so x is not really interesting here. But the intercept here on the y-axis is beta naught, and the data are distributed about that point. Great. So beta naught equals 5, at least when we estimate it. So once we've got this is our model, the data are vary around a true value of mu plus error, but then we draw a sample, and so the population has a true value of mu. We draw a sample, we estimate the mean for that sample, and that becomes mu hat. Our residuals then also become estimates, and mu hat is beta naught hat. And so 5 is our sample estimate y bar. Okay. So that's so our model here then, just to rewrite it one more time, I'm running out of space for my hand, is yi hat equals beta naught hat. And that happens to be equal to 5. All right. So, simple enough. All we've done is call the center beta naught. So, take a paper off. All right. So, part 2, we need to understand what an indicator function is. Folks in other fields call these dummy variables, a term that I despise. I think indicator variables are much better for a couple reasons. One is you don't use the disparaging word dummy. The second is you use a word that actually tells you what it does. It indicates things. So an indicator function is either 0 or 1. Those are the two possible values. So the notation is a capital I, parenthesis, and then a random variable x, which takes certain values. And let's say it can take a value a, or it could take a different value. So this whole indicator function equals 1 when x equals a, and it equals 0 when x does not equal a. And that's going to be great, because when we add groups, we can then use the indicator function to indicate which group observations belong to. So let's look at one more simple example before we move to Anova. Let's make the case where we've got yi, or y hat, and we've got different groups. So how about levels of factor 1? So factor 1 can take level 1 or level 2, making a little table. And the mean for the first group will be 5, and the mean for the second group will be 4. So I'm going to draw this picture now. Okay. So we've got factor 1, and it can take levels 1 and 2. And let's see, do I have enough space? Let's have it 1, 2, 3, 4, 5. 2, 4, 5. So for group 1, the mean is 5, so that's this value here. For group 2, the mean is 4, that's this value here. And I'm going to ignore all the variability, all the observations. These are all the predicted values y hat. So we want to write a model that allows for all these groups. So we can write y hat equals, we've got a baseline group, which is the first group, beta naught, plus, now here's where our indicator function comes in. We're going to do beta 1, or maybe I'll call it beta 2 because it's group number 2. Doesn't really matter what these are called. Beta 2 times the indicator function when factor 1, so why don't we call this x, okay? When x equals 2. All right, so this equation becomes two different things. When x equals 1 and when x equals 2, we get two different equations. When x equals 1, we have y hat equals beta naught plus, because x equals 1, the indicator function, this whole thing, equals 0. So that's just beta naught. When x equals 2, we have y hat equals beta naught plus x equals 2. So this indicator function equals 1. 1 times beta 2, beta 2. Beautiful. So let's go back to our table. Our table, we've got y hat for group 1, it equaled 5. Okay, so beta naught equals 5. So I'm going to rewrite that over here. For group 2, the mean is 4. So how do we get this equal to 4? Well, that's 5 plus something equals 4. You guessed it, minus 1. So beta 2 is a minus 1 times the indicator, x equals 2. And that is our model equation. So we have beta naught equaled 5, beta 2 equals negative 1. Let's look at what that looks like on the plot. So we have beta naught, which is 5, and then beta 2 equaled minus 1. So beta 2 is that value. It's the offset from the baseline group to the second group. So that equals minus 1. So that's the basic idea. And the only thing that happens from here is that things become more complicated. So we'll still use these indicator functions to specify categories as offsets from the baseline group, and then we'll just write out model equations using those indicator functions. All right, so let me tear away. All right, little ink bleed through. And we'll bring up our first example. So in this first example, we have 3 levels in a one-way Anova. And we want to write out what the model equation is. All right, so I'll just get enough to have that table on here. You know, I'll probably reproduce the table. All right, let's reproduce the table. So we have the level of the factor, 1, 2, and 3, and the means are 5, 4, and 6. Okay. So I'll get rid of this piece of paper now. So let's start off by plotting the data. So we'll say x takes levels 1, 2, and 3. The y-axis here is 2, 4, 6. All right, and then I'll just plot the points. 1 is 5, 2 is 4, 3 is 6. So we want a model equation where y hat equals, we'll let 1 be the baseline group here. And it's at this point where there's more than 2 levels of the factor where we can write this as shorthand, but then I'll show you what the shorthand expands to. So we've got a model beta naught plus beta 1 x1, okay, where x1 can take the values 1, 2, and 3. So we want to write out what this x1 expands to. So this is the shorthand. And because of the way I've got this set up, I can't actually write over here. Shorthand and the actual model equation. So we still have y hat equals beta naught plus, and then the x term and beta term expand out for all the non-baseline groups. So we're going to have, okay, I guess I called this x1, thinking ahead that we're going to have an x2 later on. So beta 1 for level 2, indicator function whenever x1 equals 2. So when x1 equals 2, this indicator function will be 1, which allows this beta 1, 2 to come into play. When x1 is either 1 or 3, this indicator is 0, and this has no effect, right? This whole term becomes 0. Plus, same thing, beta 1, 3, indicator function x1 equals 3. All right, so let's write out what the equations are for each value of x. So we're just, let's see, make some more space. So when factor 1 takes values 1, 2, and 3, what is the mean? So in this first case, factor 1, that's x1, equals 1. So let's see, we'll just walk through each step. Y hat equals beta naught plus x1 equals 1, so this indicator function is 0, times this, that's 0, plus x1 equals 1, so this indicator function is 0, so that's it. All right, how about for 2? Y hat equals beta naught plus x1 equals 2, so this indicator function equals 1, so that multiplied by this is beta 1, 2, plus x equals 2, so this indicator function is 0, so that goes away, that's it. All right, and how about for 3? Beta naught plus beta 1, 3. Nice. All right, let's go up to our plot and see how this plays out. So we have our baseline group where beta naught equals 5. Oh yeah, we didn't do that yet. So beta naught equaled 5, this equals 4, and this equals 6. So what are our betas? Beta naught, so this is y hat equals 5 plus, so how do I get 4 here? This has to be a minus 1, indicator x1 equals 2, plus, how do I get up from 5 to 6? In this case, beta 1 has to be a positive 1, indicator x1 equals 3. All right, and we're going to see these model coefficients up in this plot. So beta naught equals 5. When I go from level 1 to level 2, I get down to 4, and I do that from the baseline group by going down 1 unit, so minus 1. So that value is beta 1, 2. Similarly, to go from level 1 to level 3, I go up 1 unit from 5 to 6. And that is beta 1, 3. And then we can actually, so notice that all of the coefficients, right, are relative to the baseline. But we can ask other questions. For example, what's the difference between group 2 and group 3? Well, we can do that by looking at that difference. So between group 2 and group 3, that would be beta 1, 2 minus beta 1, 3. So that would be a minus 1 minus a positive 1, which is minus 2. So there's a 2-unit difference between those two groups. All right, so that was the one-factor ANOVA. What I should have written on the top of the page at the very beginning. And that's that example. That's a good start. I'm going to break the video here. We'll come back and do two-way ANOVA without interaction and then with interaction.